Thanks a lot. So just a little bit of background for those of you who don't know me. My name is Armon, and you'll find me all around the internet as just Armon as well. And I'm currently work at HashiCorp, where we're a DevOps tooling company, and we're working towards a software-managed data center. You probably recognize at least one of our open source tools. We make Vagrant, Packer, Surf, Consul, which we're going to talk about, and Terraform. And today we're talking about doing service-oriented at scale. So when we talk about service-oriented, the first thing that's kind of in our way is the alphabet soup that we now have in this kind of space, right? So, the old guard, maybe starting in like 2000s with Java, we started talking about service-oriented architectures. Now the new hotness is microservices. We've all groaned over monoliths at some point. And then there's kind of the agnostic end-tier architecture, which no one knows how to feel about. So the way I like to think about it is basically SOA is a spectrum, right? As it's not a binary decision. On one end, you have your microservices, which, there's varying definitions. It's basically the smallest unit of your service, maybe 100 lines of code, maybe one network function. But basically the smallest thing that can do anything useful. And then at the other end, you have your monolith, which is let's just shove everything into one super project and not deal with anything, right? And so that's kind of the full spectrum of choices you have. So I'd argue that there's kind of a utility curve that looks something like this, right? You run the risk of if you have everything being a microservice, then you introduce a lot of overhead, both in terms of conceptual overhead, which is, okay, I have to think about my 1,000 different services and what they do, as well as actual network performance overhead, which is I'm probably making 500 API calls to do one page render. So there's a loss of utility on one side, and then on the other side, if you have too few monoliths, basically maybe two epic services, then it's still very hard to reason about application changes within that code base because the scope is so large and very interconnected. So really, we want to be somewhere in the middle of this curve. And then there's the kind of the end tiers, which I think are best described through example. The most obvious example is kind of our standard 2-tier. You have your web service, you have your database, maybe they're on the same machine and it's just a LAMP stack, whatever. And then, kind of the natural evolution is let's separate our business logic from our presentation logic. We'll add an API tier, and now we're at a 3-tier architecture. And then, over time, this 3-tier evolves naturally into an N-tier architecture, right? You start having different use cases, so you introduce new backends. So now you have a SQL system and a NoSQL, and you have caches, and you start splitting business logic among different services so that you don't have one massive API. And then eventually you're like, okay, well, we need to cater to mobile differently and cater to client APIs. So all of a sudden you started with 3 services and now you have a matrix of many. So the broad goals of moving towards a service-oriented architecture, there's many different definitions of it, but kind of these are the 3 that I like to think about, which is you want your service to be autonomous as much as possible, right? You don't want it to depend, you don't want every service to depend on every other service in your network. You want the scope of each service to be well-defined but limited, right? The distinction is key. You can't, if you define your service's scope as twitter.com, then you could still just make a monolithic service, right? It's not a very useful definition. And you want a loose coupling so that if one service fails, it doesn't take down every other service. Services should be able to gracefully handle their dependent services being down. So the benefits of moving to an SOA model, there's a handful of them. One, we're able to develop faster because you can develop in parallel, right? Each service can be iterated on independently, and you kind of have interfaces which are your compatibility layer. So you promise not to break your network interface, and your internal details you can iterate on in parallel. They allow you to kind of compose services together. So before in our N-tier example, we can make use of the same billing service in both our desktop and mobile presentation without basically having to duplicate this logic now in 2 different presentation layers. We get failure isolation. So if our billing service goes down, maybe users can still log in because the user service is up, but they can't purchase things. And maybe that's an okay situation. Each unit becomes a lot more testable because each service has well-known inputs and well-known outputs. So it's a lot easier to test. And we can move towards a scale out instead of a scale up because now we can actually reason about the performance limitations of every service as opposed to one enormous super monolith. Now that said, there's a reason we're not all writing service-oriented software, which is that SOA is hard, right? Otherwise, I wouldn't be giving this talk. there's a lot of challenges involved with SOA. The big four that I'm going to talk about today are basically discovery, monitoring, configuration, and orchestration. So we're going to unpack what each of these is. Discovery is kind of the most immediate problem you run into when you move towards a service-oriented model. You have your web tier, you have your API tier. How do they find each other? How do you route traffic between the two tiers? So this is kind of the discovery problem. How do you discover your other co-services? Well, one obvious answer, which should be obviously terrible, is the hard-coded address, right? And the reason this is a terrible system is that it's, A, completely inflexible, right? If that machine dies, then the system is hosed. If you need to have more than one API tier, you're in kind of a nightmare situation, right? So this struggles from problems of both scalability in terms of operations, and it also suffers from fragility. So another answer, which is slightly better, is basically the hard-coded load balancer address, which is, okay, I want the freedom to be able to scale my web tier or my API tier. I don't want to have to update every web service, so I'll just point it at a load balancer, and this way we only have to update our load balancer when we add and remove servers. And moreover, our load balancer can do health checking for us, so that if we lose an API node, the load balancer will just stop routing traffic to it. This definitely improves the situation a little bit from before, but we still have the problem of now we have a single point of failure, which is our load balancer. We still have the problem of if we lose the load balancer, we have to update that hard-coded IP address. So really we've reduced the problem, but we've just kind of hidden it under the rug. The next problem is if we're depending on our load balancer to do that health checking for us, and we remove the load balancer, well, now we've moved that health checking problem to be the applications problem, right? Our web tier somehow has to know, hey, I have 3 different API servers to choose from. One of them is unhealthy or down, the other one is degraded. How do I route traffic only to the healthy nodes or load balance properly so that I'm not overwhelming particular nodes? The next big challenge, which is a little orthogonal to the other two, is configuration. Assuming I now have my scale-out web tier, they all have configuration, and I want to be able to update this dynamically, right? So, the answer for a long time is just use static files. Great, that's fine until I want to change my configuration. A lot of people use config management tools. You also suffer from problems of needing to wait 30 minutes for things to converge, which may or may not be okay for your particular application. And the last one is basically orchestration. So suppose you're suffering from, the nth OpenSSL vulnerability, and you need to roll out updates across your network. You might need to basically invalidate all of your sessions and rotate your session encryption key. So you really want to be able to broadcast a message to your presentation tier and say, hey, rotate the key you're using for session encryption. You want your user service to be able to invalidate all of the sessions, and maybe you want to talk to your backend cache and tell it, hey, you should be purging everything under this key prefix because they're potentially compromised. So doing this orchestration at scale is also a challenging problem. So basically, there's definitely clear barriers to service-oriented. There's challenges there. There's a reason we're not all doing it. As we've seen, these are all real problems that you have to solve if you want to be able to do service-oriented at scale. That said, none of these problems are new per se. So there are existing tools and solutions to all of them. So in kind of service discovery world, there's probably the richest tooling because this is the most obvious, most immediate problem. You got your DNS, Zookeeper, you can home roll something on a SQL system or Redis. But ultimately, it's kind of like going to your realtor and saying, I really want a house. And your realtor instead takes you to Home Depot and hands you a nail and hammer and says, well, you can build a house. Just pick anywhere you want and build your house, right? Also, there's no plans included, so just figure that out on your own too, right? So it's not exactly what we're looking for if those are our challenges. Similarly, monitoring has been a big problem forever. It's not a new issue. So like I said, we can rely on load balancers to be doing application-specific checks. Nagios and Sensu are very broadly deployed. But they suffer from a different problem, which is they basically act as knowledge silos, right? The goal of Nagios is not to feed information back into your service discovery tool. The goal of Nagios is to page someone, right? It's to page a human being who reacts at the speed human beings react. So in this sense, they generate all of this health information knowledge, and then they silo it away for their own personal use. Again, not what you want if you're building a service-oriented architecture. You want to know this system is down, stop routing traffic to that system. No worries. The next problem is configuration. Like I said, the moment you write an application, it takes some kind of configuration. This is now a problem you have. The answer for 99% of systems is probably to throw down a static file. Not a great answer. It's getting slightly better lately. Configuration management tools have improved this dramatically. At least it's now possible to change these configurations on some interval. Again, you can always home roll something on SQL and Redis yourself, but again, that's kind of the nail and hammer approach. Not necessarily great. Orchestration, I'd say, is probably the least well-solved problem because it's the easiest to ignore, right? If you don't build a complex system to solve this, well, you can easily just be like, well, in the case OpenSSL has a problem, we just spend 2 days dealing with it, basically. So there are tools. Again, probably Parallel SSH is the most broadly used. There's a few other systems, but mostly it's like roll it yourself. So to this end, we kind of looked at this problem space and we're like, is there a way we can do this better? Can we take all of these problems and solve it in one blow? And that's kind of why we decided to build Consul. We're like, everyone is reinventing this wheel. We've reinvented this wheel 3 times ourselves. We're kind of sick and tired of doing this. Can we just do it once and for all? So with Consul, we really wanted to take a solution-oriented view of this problem as opposed to a tool-oriented view. We wanted to give you the house along with its blueprints and the hammer to be like, you know what, if you don't like the location of that wall, feel free to knock it down and move it around, but you don't have to build the house yourself, right? You can just set it up, hit go, it just works. And so to that end, it tackles all 4 of the problems we've discussed. And so I'm going to dive in a little bit more and see kind of the approach Consul takes with all of them. So service discovery is kind of the beating heart of Consul. This was the reason we started writing it, and it kind of grew out of 2 of our other attempts. Surf is one of them that's public. Polaris was a failed internal attempt to solve this. And basically, it thinks about your infrastructure and kind of the abstraction of you have nodes. Nodes are able to run services, and services are monitored with checks, basically. So doing a service registration just requires a very simple JSON body that describes your service. And then the discovery side of it is done either through DNS or an HTTP API. So as an example, here's a JSON body of what it would look like to register a Redis service. So here we're just telling Consul, hey, I have a service, its name is Redis. I'm going to tag it and say this is a slave node, tell Consul what port it's running on, and give it a script to basically check that Redis is alive and running. So I'm just going to take a moment to note that the checks are all Nagios compatible. So, you know, any one of the like 10,000 checks that have been pre-written, you just throw it at Consul and it just works. So we throw this at Consul, and this is enough for Consul to be able to register that the node is now providing the Redis service and checking it every 10 seconds to make sure Redis is alive. And then we can do the discovery using DNS, right? So DNS is a first-class citizen for Consul's service discovery. So here what we're going to do is just do a DNS lookup. So the service.consul is kind of a magical TLD that tells Consul this is a service lookup. And the slave.redis is saying look up all instances of Redis, but then only return the ones that are tagged as being slaves. So it's possible that I have a master-slave situation and I only want to be talking to the slave node for whatever reason. So then Consul will return and say, oh, here's the IP address of a node that I know is running this. And you'll notice it returns a TTL of 0, so that the next time you ask, it can actually return a different answer and load balance across the different instances. This is great. We have an IP address, but we don't have a port. So one way of getting around this is actually to just respect the DNS standard and ask for an SRV record. So an SRV record basically includes the port information with the result. So now we're doing the exact same query to Consul, but instead of doing an any type request, it's an SRV request. Consul properly returns, go to port 8000, here's the IP address of that node. So in this sense, the DNS interface gives us a zero-touch approach for doing service discovery, right? I didn't have to write any application code to register my service. I didn't have to write any application code to discover the location of Redis. I simply gave it one JSON file, started issuing DNS queries, and boom, I have service discovery working, right? And for free, I'm basically getting randomized DNS, which kind of acts like round robin. So if I have 100 web nodes, they're basically going to get, on average, 1/100th of the traffic. And so I get free load balancing. And on top of that, Consul automatically filters on the health check status. So if I have those nodes and 20 of them are in an unhealthy state, they just won't be returned as a result and so traffic will just route away from unhealthy nodes, right? Again, you just get all of this without actually having to write one line of code. Should you choose to write code, it does have a richer HTTP API that you can use. So this lets you do deeper integrations to console, build more intelligent clients. Maybe you want to do connection pooling or more advanced load balancing or whatever it may be. You can make use of its HTTP API to integrate that. So it doesn't silo the knowledge away from you. It really wants you to be able to integrate it into your systems however you want, right? Feel free to use the hammer and remodel the walls. In terms of monitoring, we, again, took a look at systems like Nagios, and we're like, okay, we want a system like Nagios, but we don't want it to struggle from the same scalability challenges, and we also want it to be DevOps friendly. If any of you have actually tried to do a DevOps-friendly Nagios, you've realized the pain and suffering that is, and we're like, we have to avoid that. Additionally, Nagios data isn't actionable by the service discovery layer. It goes into some UI, someone gets paged, but it's very difficult to actually react to that. So we wanted our monitoring information to actually be actionable and integrate with the rest of the system. So to that end, we kind of take a different approach when it comes to monitoring. We run the checks directly on the end nodes, so we don't have a notion of basically, the split is a push versus pull. So Nagios uses a pull model, which is it will SSH into all of your servers, run the checks, and then pull the status back in. Consul flips it around and does it the other way. The clients actually run the checks and then push their state information into the servers. One major difference is this allows us to move to an edge-triggered model, right? So one observation is that checks tend to be very stable, right? If a check is in the passing state, it tends to be in the passing state for hours, weeks, days at a time. And once it goes to the failing state, it tends to stay in that state until you react. It's more of the edge case or pathological case to have a check that's going between passing and failing on every check interval. So one optimization you can make when you move to this push model is you actually only push changes to the server. You don't push an update every 10 seconds. You push the initial one that says, Redis is alive, and if the status changes, I'll push to you and tell you, right? So the servers are free to assume that there's basically a stable state unless they hear otherwise. Now this, of course, introduces a different subtle problem, which is one of liveness, right? If you don't get any updates and you're the server, you don't know if the checks are simply stable or if the agent is just dead, right? Both are possible. It could be that I'm not hearing about Redis because the whole node is down. So to work around this limitation, we basically make use of a gossip-based failure detector. So I'm going to talk a little bit about this in a little bit, but what this allows us to do is move away from having heartbeats entirely in console, and we're able to actually, this gives us a number of things, which is one, we get our edge-based change detection, which is like 2 orders of magnitude reduction in write from Nagios, and we also have a constant load on our servers regardless of the size of our cluster. So with Nagios, I'm sure you've seen your uptime slam to like 5,000 by the time you have like 100 nodes. With Consul, you can have a 5,000 node cluster and your servers are effectively idle because they're not doing a very expensive pull operation every 5 seconds. The next kind of piece of the puzzle is configuration, application configuration. So Consul provides a hierarchical key value store. You can access it using a REST API. It does long polling for changes. So if you want to be able to block and be like, I need to know the moment my application's configuration is updated, you can do that. It provides distributed locking. It gives you ACLs. So it kind of gives you a whole toolkit of features to be able to build configuration and tooling around it. So 2 examples I like to give. Again, these are totally zero touch when you're using Consul. One of them is envconsul. So envconsul basically allows you to set your environment variables from keys in Consul. So as an example, if I have a foo service, maybe I set envconsul to basically read the keys from a certain prefix, service foo config, and those just get set as environment variables, and then my process is invoked. I just put ... because at that point foo is running. Now because we've given it the reload flag, if we detect a change in the configuration, we can send a sig term, wait for the process to quit, and then restart it with its new configuration. And in this way, we're able to basically almost instantly get a real-time updates to our configuration. This is just an example. If you pass it through env, then you can just see the list of environment variables envconsul might be setting. So in this case, maybe we set max cons and environment. Another way to integrate is basically consul-template. This is a generic templating tool. So you give it an input template, you tell it an output path, you give it a reload command, And because it's just doing files on disk, it lets you integrate console with just about anything, right? Almost any tool that's written can read its configuration from file. And so consul-template provides a bridge that lets you populate that file dynamically. So an example that we use very often and we use internally is basically dynamically configuring HAProxy. So for example, I might have a backend definition and I want to get my maximum number of connections from the key value store, and I want to get the list of services that are part of this front-end service. So I have some front-end service, and I want to iterate over the tag app. So app.frontend is basically saying, find all the nodes that are in the front-end service, make sure they're tagged with app, and then populate this. And consul-template will emit something that looks like this. So this HAProxy config gets emitted to disk, we reload HAProxy, and now we have HAProxy dynamically being configured by console. Again, we didn't have to touch any of the code inside HAProxy to do this. And the last major piece of the puzzle is orchestration. So console provides probably the largest toolkit for this because it's the most challenging problem. And we're just gonna cover each one of these in order. Sorry. So watchers are kind of a way of, well, as intuitively they're named, it's a way of watching for changes, basically. So what watchers do is pair a view of data in console with a custom handler. And so when I say a view of data, there's a lot of different data in console. So there's key value data, there's services, there's nodes, there's checks, there's events. So you can basically configure your watch as to what view of data you care to observe. And then you can set up a handler. This can be done either statically or dynamically. What I mean by that is you basically don't have to specify ahead of time what data you're watching. You can come in later and decide, oh, actually, I do care about the list of nodes. It doesn't require configuration ahead of time. So a really simple example of this is, suppose I just want to watch the list of nodes in my cluster, right? I can just specify console watch, and type is specifying the data view I care about, so that I'm caring about the node's data view. So when you run it with no handler, it just emits the current data. This is the current state of the world. Alternatively, you can run it with a custom handler. In this case, maybe setup DNS is used to reconfigure bind on the fly. So all this is going to do is just going to run perpetually. As soon as there's any change to the list of nodes, we're going to reinvoke our handler, and it's going to be able to dynamically reconfigure bind. And again, we didn't have to really do a lot of complex plumbing. We just have to read JSON from standard in, and that's about it. The next system is console provides a flexible event system. This is just a name and a payload effectively, but it lets you do almost anything you want because of its integration with the watching system. In addition, it blends in use of the service catalog information, so the knowledge of what nodes are, what services are running, the nodes, and the tags can be used to filter which nodes receive certain events. And all of this is layered on top of the watch system. So here's an example of that. Suppose I want to fire an event that is only received by the Redis service. Well, you just call console event, and then you filter by the Redis service. And in this case, we're going to name our event test, and we're going to give it a sample payload. And on the other side, console watch can again be used to receive and handle this event. So on the other side, we're doing a watch. This time our data view is an event type. We're only looking for events named test, and our handler is just cat so that we can see what's happening. And boom, we can just see that, oh, cool, we got the event triggered on the other side. So in practice, what you might do is set up an event that is like, purge my caches, and it knows to connect to the local memcache and tell it to flush. Or it knows how to tell your API tier to rotate its encryption key. But you're able to basically customize this however you like. Building on top of that is kind of giving you the ultimate hammer, which is a remote execution framework. So this is layered on top of the event system, and you can think about it as basically being parallel SSH++. So it again blends in information from the service catalog, so you can filter on services, nodes, tags, all of that data, but you don't have the same kind of limitations of parallel SSH. So again, using that is super simple. Let's say we want to target our Redis nodes. We want to just run the uptime command on all of them. Just run console exec, filter on service, run uptime, boom, it streams all of the results back to us. Distributed locking is probably the highest touch orchestration it gives you. It's built into the key value store to let you safely implement distributed locks. To preempt the question, you can do locks that are both safe and locks that give you liveness. So this is configurable and up to you. If you go with the safety route, yes, there's false positives. It's all documented. You can also implement semaphores. So if you want to guard access to a resource, you only want 3 machines at a time dequeuing emails or something. You can implement that using the client-side locking. So really, the focus here was to just not go into too much detail on each one of these, but just to do a high-level tip of the iceberg as to what Consul's approach is for each of these, right? The details are documented heavily on the website, so I recommend checking it out. But the point is to show that really it's a solution-oriented approach to each of these, right? And Consul tries to weave all of them together as much as possible and to provide an answer that is as little building it yourself as is possible, right? So by using some Consul as well as the tools in the surrounding ecosystem, you can really get away with writing very little code. I just preempted the slide a little bit, but yeah, so it's the goal is to provide opinionated solutions. The goal is not to cover the 100% use case. Yes, some people have very pathological use cases. It is not our attempt to support that. We want to cover the 95% case, and for that 95%, we want you to have a it just works experience, right? You installed it, you deployed it, you run it, and you're pleasantly surprised that console exec just worked, right? In that sense, we want to just give you the house, not just the hammer. So in this way, when you think about it as a solution-oriented approach that kind of provides all of these, we like to kind of think about Consul as actually being the data center control plane, right? It is the one answer that provides all of the configuration and orchestration needs for the data center. And so thinking about it in that way, it comes as a batteries included control plane. It's not something where you have to figure out how do I patchwork different systems together. It scales to thousands of machines. So you can start deploying it when you have 5 servers, continue to use it when you're at 5,000 servers, and not worry about, okay, along the way, do I have to re-architect my entire system while it's in production, basically. You just don't worry about it. It includes multi-data center support out of the box. So when you reach that point where you want to have multiple data centers, again, not something where you're like, now I have to re-architect my entire Zookeeper system. It just works. And it provides basically a backbone on which you can build the rest of your infrastructure without having to figure out how you're integrating all of these pieces together. So we've talked about the what and the why with Consul, but not the how. How do you actually use it? So it has an agent per machine model. Each agent can be either in a server or client mode. The binary is the same, so you don't have to figure out deploying different binaries. And you need 3 or 5, I should say, servers per data center. You can run it just with one if you want to play with it and for toy cases. And at a 10,000 view level, this is kind of what Consul's architecture looks like. So maybe we have multiple data centers. Each data center contains maybe 3 server nodes and n number of clients. The servers internally will elect a leader. This is all under the covers, and the client is not aware there is a leader. And so there's some amount of data replication happening between the servers. Clients are only doing RPC requests to the servers, and you can see there's kind of some request forwarding arcs. So requests are always serviced by leader nodes. If you ease off some of the consistency constraints, other servers can also answer your questions. And because of this architecture, clients are actually able to make a request without even knowing what data center they're making a request to necessarily. So a client can transparently make a request to a different data center, and the multi-hop routing just happens automatically for a client. You just specify, hey, I want the list of nodes in data center 2. The client doesn't have to figure out how to do that. Consul will forward the request down the right paths and get that data and return it. So every agent is responsible for running an RPC, HTTP, and DNS interface or API, right? This interface is exactly the same whether or not they're a client or server. So as a client of Consul, you don't have to care basically what is the address of the server or who should I be directing traffic to. You always talk to your local Consul agent. All of the agents run the health checks locally, as we talked about. Event execution, that is also local. And they're part of this gossip pool. So I hinted at this earlier. So the gossip pool is based on a different project we have that's called Surf. And it provides 3 main utilities to Consul. One is membership, the failure detector, and the event system. So the membership is actually very important in terms of simplifying the operations of Consul. When a node joins a Consul cluster, you don't have to hard code the address of like your Zookeeper servers or whoever the authoritative leads are in the system. You just join any other peer, whether client or server, and through the gossip layer, they discover the addresses of all of the server nodes, all of their peers, And so as an operator, it's very easy. If you lose a server, you can just boot a new one at a different IP address. You don't have to go through and reconfigure 1,000 nodes to be like, update your Zookeeper IP address. It just happens automatically. So the server discovery is totally automatic, and it also allows us to do protocol versioning underneath the hood without users dealing with this. So in the short lifespan of Consul, we already have 2 different protocol versions, but you can run the 2 simultaneously in the same cluster, and the clients are smart enough to figure out what to do without you needing to configure that. All of this is passed around as part of the gossip layer. The failure detector is really important, as I hinted at before. It lets us distinguish between nodes leaving the cluster by choice and nodes that have failed. Why this is important is if you choose to leave the cluster, it allows us to automatically reap data out. So you don't end up with a lot of garbage buildup inside of the service registry. If we know a node left and it was previously providing some services and health checks, we're able to delete all of that out of the catalog for you. If a node has failed, we're able to know that and then automatically try and reconnect to it and rejoin it when it does recover. It also allows us to build distributed locks that have liveness properties. It allows us to avoid heartbeating the way that Nagios and Sensu have to do. And more importantly, it lets us have a constant load across the entire cluster. So the servers aren't doing any more work with 5 servers as they are doing with 5,000. They also provide an event system. So this is the kind of the underpinning for Consul's event system. The messages are delivered in a peer-to-peer way. And because of this, we don't have the central servers that have to manage delivery and broadcast of messages. So even with enormous clusters, we basically get sub-second delivery of events very reliably, even during packet loss conditions. So that's kind of what all of the agents are responsible for doing. The server nodes are a little special because they have an additional burden placed on them. They own the centralized state. So all of the state information about a cluster is held by the servers. So all of the queries to that get forwarded to servers. Clients basically are stateless. So they're also responsible for query handling. The data is replicated using the RAF consensus protocol. And they also the server agents only sit in a specific WAN gossip ring. So this is how all of the data centers can be aware of one another. Data center 1 and data center 2 are linked only by their server nodes. So this way, even if you have 20 data centers, you don't have to have every client know about every machine in every data center. Only the servers need to know a small bit of additional metadata about the servers in the other regions. And they can do the appropriate request forwarding. So because of Consul's model of needing your agent to be ubiquitously run, and every agent having a unified API, you can kind of start to think about Consul as being a system service in a way. Because once it's deployed to every machine in the data center. And this model of thinking is actually very useful for both operators and developers, because you can begin to write applications and administer your systems assuming Consul is there, in the same way you just assume syslog is present on your machine. And so this actually makes it, provides a set of facilities that applications can depend upon to provide things like coordination, configuration, storage. So this is great that all of this is kind of Consul in abstract, Consul in theory. So I want to spend a little bit of time on Consul in production. The popularity of Consul so far has been pretty staggering for us. I think it has well over 2,000 stars on GitHub now, over 100,000 downloads. It powers our personal VagrantCloud, which I'm going to talk about in a little bit, and also several very large-scale customer deployments. So VagrantCloud, for those who aren't familiar, is a SaaS product that HashiCorp has around Vagrant. It powers the Vagrant sharing feature, which lets developers share their Vagrant environment with each other. It powers box discovery, so if you're looking for Vagrant boxes, and it lets you host your Vagrant boxes in the cloud. So if you want to share a Vagrant box with your dev team, all of that's kind of part of this product. And its whole backend is a service-oriented architecture, right? So Consul is deeply involved in this service. Right now it's deployed to a single VPC in Amazon. It's composed of dozens of services, some of which are internal that we've written, some of which are external, like Heroku Postgres, and we deploy it with 3 Consul servers. So discovery in our Vagrant Cloud is actually almost entirely powered by DNS. There's a few services that are a little more intelligent, so they use the HTTP API and query the local service. One example of this is when you're uploading large Vagrant boxes to us, you're uploading maybe a 50 gig binary. We'd prefer to keep that stream local to the box. So we're able to basically do a local lookup to the agent and be like, is there any processes locally that can handle this so that we don't have to route it over the network? So that's an example of maybe when you want a more intelligent client. And then we use HAProxy at the edges of our network. So that kind of looks like this. And the reason you do that is consul's really designed for internal service discovery. It's very difficult to have Route 53 query into consul and say, hey, what server should I be routing to? It's, external DNS providers want to just route to a single or a few well-known IPs on the outside. So HAProxy is kind of our bridge from the outside world to the inside world of consul. And again, we use consul-template internally to dynamically configure these HAProxys. So although we're using HAProxy for, getting into the network, it's still being configured as part of the same system that does everything else. Our application configuration, probably not surprisingly, is done using consul-template and envconsul. Consul-template's mostly used for kind of, I'd say, legacy or external systems that we didn't write personally. Most of our internal services are designed to just be able to read in through environment variables, and so we just depend on envconsul. This makes it really easy to also test in development because all you have to do is set a bunch of environment variables. There's not a lot of complex setup there. And the way we manage setting these keys is using the consul web UI. So consul includes a web UI that lets you see your services and nodes and manipulate the key value store. And so, we didn't do anything fancy. We just set our configuration in there and go into a web UI to manage it all. But probably where consul is most deeply ingrained is doing the orchestration for VagrantCloud. So it manages both the deploys, leader election, and service coordination, which I'm going to talk on briefly. Deploys are totally event-driven for us. So we have events that will trigger downloads of the new binaries of given services, and then a separate event that'll trigger the rolling restart of them. So simple enough, we just trigger one event, binaries everywhere. Whenever we're happy and we're ready to roll out, trigger the next event and do a rolling deploy. Client-side leader election, again, a very useful feature because it allows us to do highly available services by doing just an N+1 style deploy. So where we know we might only need one instance of a service, we would like to have higher availability than if that service dies and we lose it. So we'll do an N+1 and deploy 2 of them, and then do client-side leader election to figure out which service is actually serving traffic. So when one dies, the next one can pick up where it left off maybe 15 seconds later. And so in this way, it removes a huge ops burden of us getting paged and having to wake up at 2 in the morning. It's kind of like, well, you just wait 15 seconds and it fixes itself. And the last one, which is kind of the one I'm most excited about, is kind of doing service coordination within the services, right? So one service that we have is Storage Locker, and it's basically our blob storage service. So like I said, people are uploading giant binaries to us. We use Storage Locker to manage this, and so it provides a simple put, get, delete API internally. Now one problem it has is when you're uploading a 50 gig image, most backends that you might want to store to can't actually handle that. So you're doing multi-part uploads. So you're taking one giant 50 gig image, chunking it into 100, 500 meg parts, and then doing those uploads. Well, the problem is that with this approach is that you can end up with partial failures, right? The client loses internet connection 25 gigs in. We've already uploaded 25 gigs. How do we manage the cleanup of that? Similarly, when you're deleting the file, we might delete, half of the contents, and then the other half failed to delete, and now we have some bizarre partial state, basically. So the approach to this is kind of a little bit taken from the database community. We basically add a write-ahead log to the service. And so the write-ahead log, Storage Locker declares ahead of time, these are all of the pieces I'm about to upload, or these are all the pieces I'm about to delete, and this allows us to gracefully recover. So as an example, I won't talk about all of the pieces here, but when the request comes into store, Storage Locker will create a wall entry within consul. This wall entry will include all of the parts it's about to upload or delete, and then we begin uploading that to whatever backend is configured for that particular key. So we might upload some of the parts. If we're successful, great. We commit the wall log entry by simply deleting it out of consul. The transaction is done. If we encounter an error, something fails, we can trigger a rollback by simply deleting all of the parts that we've already uploaded, right? But where consul helps us even more is we can actually not only handle a failure of the client, so if the client leaves in the middle of the upload, we can actually handle a failure of the Storage Locker service in the middle of an upload. So the Storage Locker service itself might die. Another Storage Locker instance will detect this using the client-side locking and pick up the wall log and initiate an immediate rollback. So even if we lose the instance in the middle of an upload, we still don't end up with a partial state. We can recover within a few seconds, and we don't have a bunch of garbage lying around in S3. So in terms of deploying it within our Vagrant Cloud, it's dramatically simplified our operational pain, right? We're able to build more robust applications by depending on the primitives consul provides us, and we're getting real-time reaction to things. We're able to build highly available services that fail over quickly. We're able to update our configuration quickly. We're able to manage deploys very quickly. And all of this is done with a minimum amount of ops pain. Most of it is just throwing some JSON files on disk. So that's good and dandy. I mean, obviously, we developed it, so hopefully we use it. Does anyone else use it is the question. And so anecdotally, I can say, yes, there's been many industry deploys already. Of course, the size of the clusters follow a power tail, as with anything. So there's a few very large deployments, a handful of large deployments, and many, many medium-sized deployments. And so I just wanted to dive into two of them. So one of them, luckily I just got the email to release their name like 10 minutes before the talk, is Lithium Networks. So Lithium Networks is a very large software as a service company. They mostly sell to the Fortune 500. They have hundreds of employees in many locations around the world. And they have a pretty complex hybrid cloud infrastructure. So they have one data center that's all contains physical hardware still. They have an OpenStack cluster on premise. They also use AWS, and now they're experimenting with GCE. So they have very complex multi-cloud orchestration problems. And so they've totally deployed Consul. This is a 1,000+ node deployment. It spans 4 data centers. Each data center has a QA stage and production environment. And right now they're using it just for service discovery. They haven't quite adopted it for some of its other features. And they've already seen a 15% reduction in fleet size just by moving a bunch of those intermediary load balancers out of their cluster, right? They were on that hard-coded load balancer approach, and so being able to remove that, they were able to spin down a bunch of nodes. So for them, this has been a huge success story. Another one, which is also a cautionary tale of why you don't email someone's legal department 2 days before you need something. I can't release their name yet, but they're a very large CDN company. So their deployment currently spans 2,000 machines across 12 points of presence, or POPs. And so for them, they're adopting it totally, more than just service discovery. They're replacing Zookeeper. They use DNS and HAProxy for their service discovery. Application configuration is being migrated out of their config management tool and into Puppet, out of Puppet into KV. And this way they're saving 30 minutes convergent runs for application changes. They've already started building services that depend on Consul for client-side leader election instead of Zookeeper. And they've told us that they're able to move faster with less operational pain because they're relying on Consul now. So on the horizon, like I said, there's basically a power tail of deployments. We've already seen many, many deployments that are in the hundreds of servers case. We're now talking to a few people who are experimenting at the next order of magnitude from what we've played with. So hopefully the next time I give a talk, we can talk about some of those guys playing with it at 20,000 and 100,000 node scale. The point of this is basically that there's a common set of challenges that all of us face. Anyone who's deploying software, anyone who's considering moving to service-oriented faces these challenges. Some of them are exacerbated by service-oriented, for example, service discovery, but things like monitoring, configuration, orchestration are universal, even if you decide to go with a monolith, right? And so what we tend to see is basically a system of patchwork solutions where people are reinventing this problem in-house all the time, right? And when you do that, you tend to have to choose between doing it right and doing it fast. Because typically, infrastructure is seen as a means to an end, right? It's not a value add in itself, so every hour spent on it is an hour lost on the product. So in addition to building your own in-house thing and probably doing it fast, you have to now be burdened with maintaining this tool. And generally, you end up with a tool that is basically minimum viable as opposed to being maximum utility, right? And so this is where we see Consul fitting in. Consul can kind of be your data center's control plane and provide that maximum utility instead of the minimum viability. And so it comes batteries included. You really don't have to write any code to get started with it. Throw some JSON files in, start using template, and you're good to go. It works at scale. It's been designed to run at scale. It's been tested at scale, and we're testing it at ever larger scale. And it lets you build more robust, more reactive infrastructure. And with that, I'm going to wrap it up. Thank you. So if there's some questions, I'd be happy to answer. So there's a few options. TLS is the big one. So right now it supports full PKI stuff. You can just give it a certificate authority, and then you're just doing client-server keys, basically. And then on top of that, there's a token-based ACL system you can use. So you can it's similar to Amazon IAM, basically. So you can kind of restrict key prefixes and be like, okay, if you have this token, you can read and write from these ranges. These other ranges are denied. And so we're hoping to broaden the use of the ACL system to let you kind of even restrict service discovery down as well. Yeah, that's a great question. Basically, the default mode is, so for example, in the dig request we did, we said redis.service.consul. And so what that translates to is actually give me a Redis instance in my local data center. So by default, the default behavior is that, because we think that's kind of the sanest approach, is you probably want to be routing within your data center. And now if you want to be explicit, you can actually ask for a different data center. So you could say redis.service.eu.consul, and then you're asking specifically, go to the EU data center, find a Redis instance there, and provide that address to me. So if you really want to be doing global routing, we want that to be really obvious to the user that this is what you're doing, and so that's not the default. It's definitely an explicit thing you have to opt into. But otherwise, traffic defaults to local only. Yep.
How do you commonly handle like development parts? Do you just run like the whole console side just in your dev VM or something like that? Or
Yeah, because it's just, you can just run the server mode with like just one server, and then it acts as client server, everything in one. So it's pretty lightweight, so it's not a big deal.
You mentioned you do rolling deploys.
Mm-hmm.
Do you use the semaphores in the console?
You totally could. We actually just do something way janker. We just pick a random sleep interval. So it's just like pick a value between 0 and 30 seconds, sleep, and then do the rolling to restart. You could get fancier and do a semaphore based if you really wanted to, but time.sleep worked pretty good for us. Let me just make sure I heard it correctly. Does the leader election work over the gossip protocol?
No, so they're using two gossip protocols, right? One for local and one for plan.
Yep.
You use leader election and
Oh, okay. So the question is, can you do client-side leader election and locking across data centers? No. So currently you can't. Actually, so let me caveat that. There's basically you can get two types of sessions or two kinds of locks. One which is safe, meaning safe in the academic sense of console will never release this lock for you unless you explicitly do it. And then there's live locks, which is console will release the lock if it detects that the node owning the lock has failed, right? And the reason that's not safe is because the node might not have failed, right? And there's no perfect solution to this. So you can't get a lock that is live cross data center. And the reason for that is basically the failure detector can't work across data center boundaries. Now you can get a lock that is safe across data centers so long as liveness isn't something you need. We are working on that. Next version of console will add a heartbeat-based mechanism. So there will be the proper caveats that the performance will suffer if you're using it, but you can do cross data center locking if that's something you really need to. Yep.
the key value store, is that replicated across data centers?
No, so that's also per data center. We have a separate daemon called console replicate that will do master-slave replication. So you just point it at your source and tell it where to write to, and it'll handle doing the updates for you. But it's async replicated. Cool, awesome. Well, if there's no further questions, thank you guys.